Okay, so many time in regression analysis, we deal with the non-negative dependent variable, which is a count variable and takes only integer values, for example, 0 and so on. So this is another example of a limited dependent variable, because this variable can only take non-negative values, and those values can take only specific values. So the example of this type of data could be number of hospital visits or the number of calls received in a call center, etc. So see, number of calls received in an hour in a call center, it can only take specific count values. Similarly, number of hospital visits in an hour can only take non-negative integer values. Similar to my previous discussion about a binary dependent variable or a dependent variable with a corner solution response, OLS may not be the best estimator in this case. Why? Because a count variable cannot take a normal distribution. And we saw that one of the assumptions of OLS was that our variable is normally distributed, but in the case of count data, the distribution that count variable will fall into Poisson distribution. And we can represent the probability mass function of this type of distribution as probability that our dependent variable y will take an integer value of h will be equal to, now this e is the Euler's number, which is about 2.718. This u is the expected value of y, which is greater than 0. H is the number of occurrences, for example, the number of hospital visits, etc. So similar to the logit and the Tobit models that I discussed earlier, the slope coefficients that you will get from Poisson regression model may not be comparable with the OLS, but a rough comparison is possible. One more thing, the standard errors that you will get from running a Poisson regression model, it has to be corrected by using this formula. The summation of the estimated residuals squared divided by the fitted values, and we're going to divide everything by the degrees of freedom, and then I'm going to take a positive square root of this whole term to get the standard error of each beta coefficient. In our example that I'm going to show you next, I will show you how to correct each standard error using this formula. Okay, so in this example, I'm going to show this crime 1 data set, and we can look at the summary statistics to know that the number of arrests in 1986 is 0 for almost 2,000 observations out of about 2,700 observations. So we have a lot of zeros in this sample, and only 8 values of number of arrests is greater than 5. So the distribution obviously is not normal, and also it's a count data which is taking non-negative integer values. Hence we are going to regress a Poisson regression model rather than a linear model for this dependent variable. Again, always start with the simple linear regression model and then compare it with the Poisson model or whatever model you are using. I'm going to use this CLM function, and I'm going to pass family equal Poisson to get the Poisson regression model, and tell R that our dependent variable is count data and we want to regress a Poisson regression model. So let's compare the results. As I said earlier, although the OLS and Poisson coefficients are not directly comparable, we can get a rough estimate about the comparison. For example, the coefficient on the proportion of prior convictions is about 0.13 in the case of OLS and about 0.40 for Poisson estimate. The OLS coefficient implies that if the proportion of prior convictions changes by 0.10, the expected number of arrests falls by 0.013, right? So we can talk about the direction of the relationship and the magnitude of the relationship. And also we can also talk about the statistical significance in the case of OLS. For the case of Poisson, the coefficient on proportion of prior convictions implies that if proportion of prior convictions changes by 0.10, the expected arrests reduces by about this coefficient multiplied by 0.10, and this will give us a value of about 0.040. And we can multiply this effect by 100 to get percentage effect. Similarly, looking at this coefficient value for this race variable, it shows that other factors being equal, the expected number of arrests is estimated to be about 93.7% higher for a black man as compared with a white man with the same characteristics. We can apply this formula to get this effect. So next thing I'm going to show is I'm going to show you how to get the corrected standard errors for this Poisson regression model. The first thing I'm going to do is I'm going to get the number of observations n, and then I'm going to get y hat, which is the fitted values, and then I'm going to get the square value of the residuals by using this formula, which is original y value minus the estimated y value, and then I'm going to square it up to get square of residuals. And then I'm going to apply this formula. And using this, I'm going to get 1.23. So what this sigma value implies is that the standard error for Poisson regression should be inflated by this value. For example, let's look at the standard error for total time, which is 0.105 in the case of Poisson. It should be inflated by 1.23 or 23%, and inflating it by 23% will give us a value of 0.0185. So the corrected standard error is this, and we should use this standard error to calculate the t-statistics and the level of significance of all these Poisson coefficient values. So this is how you apply Poisson regression model in R when your dependent variable is a count variable which takes only non-negative count values. There are a bunch of other models that you can use in addition to Poisson model. Some of these are the negative binomial, the zero inflated binomial, the Heckman selection model that I'm going to talk about in a couple of videos. You can also apply Poisson pseudo maximum likelihood estimator, which is a relatively new estimator. Alright, I'll see you in the next video to talk about censored and truncated regression models.